So this lesson is just a natural extension of the previous lesson. So I figure we may as well just do it here as well. The previous one expressly identified translational and rotational equilibrium. This is where the questions are going to get a little more general. And just say there's static equilibrium. Figure it out. So static equilibrium is exactly what static equilibrium was in Unit 2. It's not moving in any direction. The center of mass is not moving. There is no spinning. So the forces are balanced, and the torques are in every direction, and the torques are balanced as well. So it's just general versions of the previous types of questions. I'm going to do. I think I'm doing almost all the examples here, and we'll go for it. It's relatively. Hopefully, you'll see that this is relatively straightforward stuff. So, example 1. There's no picture for us, so we have to draw it ourselves. A beam. We've got a beam with a length of 4 meters. Okay, cool. So let's draw that. Make it big because we're going to have to put a bunch of forces on it. It's supposed to be uniform, I'm sure. So make it look uniform. Do a better job than I did. There's my beam. We're told this thing has a length of 4 meters, so let's make it 4 meters long. It has a weight of 50 newtons. That's important, so we can start adding our forces. And it's pivoted at the middle. Well, that's cool. So put my pivot at the middle. We start adding forces. So we're not told that it's not uniform, so we can assume that it is. So Fg, we're told, is a weight of 50 newtons. So Fg is 50. There's a 200 Newton weight halfway between the pivot and one end. We don't know which end. It doesn't really matter. So let's put that weight, I don't know, let's put it, where did I put it last? I put it over here last semester. Let's draw it right here. There's the 200 Newton weight as an Fg, we're told, of 200 newtons. If this is 4 meters long, it means that's 2 meters, which means that's 1 meter. Just so we're real clear here. That's going to be 1 meter. Where should we place a 100 Newton weight to balance the beam, and what is the force exerted by the support on the beam when the beam is balanced? So we can keep drawing some more forces in here. We know that we're going to have an unknown force. I hope that it's obvious. If we've got a mass here rotating this thing this way, the mass is going to have to be somewhere over here. We don't know where it is, so let's put it right there. This thing we know has a force of 100 newtons. But we want to know where should we place that force. So this is what we're looking for here. We're looking for this distance. Okay? And then the only other force on here that we know for sure is normal force acting at the pivot, because the pivot is acting at the center of mass. So we're looking for two things. We want to know what the force exerted by the beam is, Fn, and we want to know where this thing is acting. So we're told that this thing, are we told this thing is pivoted? Where should we place to balance the beam, and what is the force? Okay, so we're balancing the beam. This implies equilibrium. Okay? So we've got, because we're in equilibrium, we've got three things. I'll write these in black. We have, I'll write it out like this, total EQ means all of the following. Forces left equal forces right. Not going to be necessary in this question because there are no left and right forces, but I'm going to put it in here anyway. Torques clockwise equals torques counterclockwise. Okay, this is how you are to think about equilibrium. So there are no applicable force is acting left and right. So don't need that. But we do need forces up equals down and torques clockwise equals torques counterclockwise. Up equals down. So my only upward force is Fn. So I've got Fn, and that's going to equal my downward force is 150 and 200. So I've got a 100 Newton force down plus a 50 plus a 200. So my Fn is going to equal 350 newtons. That is the support, or the force exerted by the support on the beam. Done part of the problem. Now we want the torques clockwise equals the torques counterclockwise. Now let's go back to our diagram. This guy is going to create a torque that goes this way. This guy's going to create a torque that goes this way. And that way, I'm going to call positive. It's important to draw these into the diagram. So, torques counterclockwise, I'm going to have F perpendicular R equals F perpendicular R. The clockwise is that guy there, so it's going to be 200 newtons times 1 is going to equal 100 newtons times D. That's that guy there. So we can see here it's going to be pretty obvious that D is going to equal 200 over 100. So that's going to be 2 meters from the pivot. Well, what does that mean? Okay, so if this is a 4-meter beam, there's my pivot acting in the middle. That's 2 meters. To balance the beam, this D needs to be 2, which means the block needs to be right at the end. Period. And we're done. Relatively straightforward. You just got to think it through step by step. I get that you guys are probably not going to be as fast at this point. That's okay. It's the steps. It's okay. Draw my free body diagram given the information I have in the problem. We're told that this thing's in equilibrium because it's not moving. Okay, well, what does that imply? Left equals right, up equals down, clockwise equals counterclockwise, and go. Each one of these things has an implication. Okay, relatively straightforward. Flip the page. Let's keep going. This whole page is one example. I know it says example 2 and then example 3. Example 3 is just, for example 2, find a bunch of stuff. Okay, so we're going to do it kind of all together, one big discussion on this whole problem. So we've got a 45 kilogram person walking out to the end of a 10 kilogram diving board. That is the mass of the board. And we're told that the board here is 3.75 meters long. The first part of the question says, what is the correct free body diagram? Let's ignore this for a second, and let's just draw the forces in. Okay. So we've got FG acting downwards from our person here. Person at the end, FG, and we're told this is 45, so let's put some values in right away because we're going to have to redraw it later anyway. 45 times 9.8, that's going to give us 441 newtons. Okay. We're not told that it's not uniform. So we can assume that the diving board is uniform. So right in the middle of the board, there's going to be FG acting downwards. So FG here is going to be 10 times 9.8. So that's going to equal 98 newtons. Now, I'm not sure if you are aware how diving boards work. It's been a long time since anyone's been to a pool. But the way a diving board works is that this pivot here, this support right here, we don't know where the pivot is yet, but this support right here provides an upward force. It acts, this here is where the board rests. You can see it when the person flings themselves off. Next time you go to a diving board, look at the board. It actually bounces at that point here. So this support exists to provide an upward force on the board. So this guy here is going to have provides a normal force for the board acting upwards. And this guy here, this force acts as a counterweight. It's not a counterweight because it's not just hanging there. It's actually attached at this end and it's attached at the ground, forcing this end of the board to remain down. So we can say that there's an applied force, I don't know what else you want to call it, acting downwards from this pivot here. This is bolted to the ground. If this isn't bolted to the ground, the board's just going to be spinning wildly, and diving boards don't do that. Okay, so that is what the free body diagram is going to look like, which means B has to be our correct answer. Okay, let's keep going. I'm going to zoom this out so we can continue looking at our picture. For example 3 says, for the board above, use the first support as a pivot. Okay, well, they're telling us this is where they want the pivot. So let's draw that in there. First support. Here's my pivot. Write a balanced torque equation and find the force exerted by the second support. Again, when you're actually asked this on a test, a quiz, final exam, whatever, they're not going to say use the first support as a pivot. You will have to figure out where you put the pivot based on what you want to eliminate in the problem. Now, they're telling us to put it there, so that's great. So let's do the problem. We want to write a balanced torque equation, find the force exerted by the second support, write a balanced vertical force equation, find the force exerted by the first support. So they're giving us, they're scaffolding us, they're telling us exactly what to do. You're not going to get that when you do the homework or the test or the quiz. So let's just do it the way we're doing it before. We're told that this thing's in equilibrium. Three implications. Force is left. Sorry, that's my phone. I gotta pause this. Sorry about that. So where were we? Yeah, right. Force is left equal force is right. My force is up equal force is down. It's supposed to be a U. And this is gonna be my torques clockwise equal my torques counterclockwise. Okay, we're going to go back up to the drawing, or back up to the picture, and we're going to add our torques in there. If this is the pivot, these two forces are going to cause torques this way. So this is going to go like this, and this guy is going to go upwards this way, so he's going to create torques that go like that, and we're going to call this way positive. Okay? So there are none. So we don't need that. Now my force is up equal my force is down. That's relatively straightforward. We're just going to work left to right. Force is up, that's Fn. That's going to equal Fa plus Fg plus Fg. So that's going to equal, the Fa I don't know, we're looking for that, plus 98 plus 441. So we're going to find Fa using my torques. No, that's not true. We're going to find, sorry guys, I screwed this up. What are we looking for here? We want to find the force exerted by the first force. We actually want to find out what Fa is here. So this is actually going to give, so Fa is going to equal Fn minus 98 minus 441. That's what we want. So I have to find Fn, and Fn is going to be found using the torques here because we put the pivot here. So my torques clockwise are these two Fg's down here. We're going to have, clockwise is going to be 98. I'm skipping the force perpendicular R bit. So I got my force, 98. Now this is 3.75 meters, so the distance to the pivot's at the end. Sorry, pivot's not at the end. Yeah, the pivot is at the end. So half of the distance to the pivot is going to be half of 3.75. That's going to be 1.875. 98 times 1.875 plus 441 times, and the person standing right at the end. So that's going to be 3.75 is going to equal my counterclockwise torques is just this guy there. The force, the torque, well, there is no torque from this force here. because we put the pivot there. So this guy's going to be Fn, and we're told that the distance here is 1 meter, so that's going to be Fn times 1. So Fn is going to equal 1837.5 newtons, 1837.5. Find that relatively easily. It's going to get plugged in there. So my applied force is going to equal 1837.5 minus 98 minus 441 is going to equal, where is that number here? 1,298.5 newtons. There's my normal force. There's my applied force. Now, it's important to recognize that if all we were told to find is the force exerted by the second support, what we could have done instead is put the pivot here. That would have eliminated the torque from Fn, and that would have just given us the torque from Fa. We could have compared these two, the torques created by these two forces and the torque created by this force, to go straight to Fa. We could have ignored Fn entirely if we'd have put the pivot here instead. But because the way the question was outlined, it specified, hey, put the pivot there, and then go do it the long way. It's important to recognize, though, if we had to put the pivot here, we could have just used the torque equation to find it. Hoping that makes sense. Okay, buckle up. Example 4 is a big one. So here we go. We've got a beam. All sorts of craziness going on here. The beam shown below is 12 meters long and has a mass of 5 kilograms. We want to find these two angles. Sorry, we want to find this angle and the tension in that cable. This is going to be fun. This is a big example, buckle up. Free body diagram. First, let's draw this thing, okay? So I'm going to create some obvious forces here. We're going to call this tension 2. Force of tension 2. And I'm going to have a force going up this way. We'll call this F. Force of tension 1, because I'm reading left to right, so that's tension 1, that's tension 2. And there's an FG. Straight downwards, okay? That's it. Those are all of my forces acting on this object here. I can draw in some components. I can make our life a little bit easier. So we're going to have a force that goes that way. We're going to have a force that goes this way. Or, sorry, a component that goes that way. We're going to have a component that goes this way. And a component that goes this way. It's important to recognize that even though I've drawn it like this, these components are technically acting at these points right here. Okay? Even though I've drawn the triangle this way, these components act where the rope is, or the cable is attached. I have to say that every semester. So there we go. Those are my components. We'll call this FT2Y, and this guy down here is going to be FT2X, FT1X, FT1Y. Okay, so I have static, oh no, I can put some more values in here. We've got we're told this is 5 kilograms. So this is going to be 5 times 9.8 equals 49 newtons. I may as well put some, so that's my free body diagram and my components. It's not obvious that we're going to use torques. I mean, it's in the torque unit, so I'm not going to, we'll just leave it there for now. What you need to recognize, though, in every question that we look at like this, the object's not moving, so we need to consider total equilibrium. Okay? Regardless of whether or not we need everything, it's important to recognize total equilibrium means left and right, up and down, and then my torques are all balanced. And we're going to need, let's see what we need here. My force is left. I'm going to equal my force is right. My force is up. I'm going to equal my forces down. And my torques clockwise are going to equal my torques counterclockwise. Now, we don't necessarily know what we're going to need here. But at this point, we're adding the concept of torques to this equilibrium stuff we looked at before. So we have to at least include it here. Hint, it'll be very useful. So I'm going to put some distances here. We know that as we're told, that we're told a few things here. We know a few things here. We know that this whole thing is 12 meters long. If this is 2 meters, this distance here is going to be, if that's 12, that's 6, which means that's 4 meters. This distance here is 2 meters. That's 4 and that's 2. This distance that's eaten up is 6. If that's 12, that means this distance is 6. Now, I haven't decided where we're going to put the pivot yet. So I just added in all of the distances. So let's write down everything we know, and then let's figure out where we're going to have to put the pivot. So if my forces left equal my forces right, we know that force of T1x is going to have to equal my force of T2x. Okay, so these two components are going to have to be equal to each other. So that's going to give me F of T1 cos phi. That is phi, that is theta. They're different variables, they're not the same. So cos phi equals F T2 cos theta. Ooh, and we're actually told what F of T2 is. That's 75 newtons. So F T1 cos phi is actually going to be equal to 75 cos theta. And this is as far as I can take that one for now. Let's look at up and down. I'm going to do up and down in a different color. If up equals down, that means F of T1y plus, this is up, F of T2y is going to equal Fg. Now I can put some stuff in there. Ft1y is going to be force tension 1 times, this is, yep, sine phi, plus 75 sine theta equals 49. Now that's as far as we can take that one for the time being. And then looking at my torques. What we want to do, here's what you want to consider, okay? You want to weaponize the pivot to eliminate a torque from an unknown force. Okay, that is always, if you're not told where to put the pivot, that's what you're trying to do every time. So let's look at what we've got here. We know this force, we know this force. So the place that makes the most sense to put the pivot is right there. Okay? By putting the pivot there, it's going to eliminate the force from this, eliminate the torque from this force here, and that means the only unknown that we're going to have is that angle. So the torques are going to allow us to find that angle relatively easily. So we're going to put the pivot right there. We're going to use pink. Okay, so if we put the pivot there, What that allows us to say is, okay, well, my torques clockwise is equal my torques counterclockwise. If the pivot's there, now let's go back to our diagram and add the torques in. That guy's going to go that way. We're going to call clockwise positive. This guy is going to create a torque that's going to go that way. So clockwise equals counterclockwise. So I'm going to have FG perpendicular times RG is going to equal FT2 we're going to put a pause right here. I want to go back to our formula sheet. Okay? We're going to add something in here now. The only torque equation we had was this guy, F perpendicular R, but we had another torque relationship that's going to end up being useful here, so I want to write it in right below it. My torque, we looked at it in a previous lesson, is going to equal FR sine theta. And this is for whenever my whenever my forces are not perpendicular to whatever object they're acting on. Okay? So this is the one we're going to end up using for this equation here, this idea of FR sine theta. Because if we look here, this tension isn't perpendicular to the beam that it's acting on. So it's going to be force of tension 2 times the distance of tension 2 to the pivot times the sine of the angle between the force and the beam. In this case, that's going to be theta. We're told it's theta right there. So now we can add some values in here. We know FG perpendicular, well, it is perpendicular already, so that's just going to be 49. We put the pivot here, so this distance is 4 meters. So 49 times 4 is going to equal, FT2 is 75. This distance to the pivot is 6 meters. And we're looking for theta. That's our unknown. So theta is going to equal the sine inverse of 49 times 4 divided by 75 times 6. So theta is going to equal 25.82 degrees. You shove that thing in your calculator, that's what you're going to find. Okay, well, that's lovely. It gives us one of our unknowns, so we can go and we can actually plug this into our unknowns, unknown thetas in these two equations here. So I'm just going to go like this. And we're just going to do that as well. And we're going to see what that gives us in both of these equations. So first, we're going to get FT1 cos phi equals 75 cos of 25.82. Whoops, that shouldn't have been there. Sorry. And this guy here is going to give us FT1 sine phi plus 75 sine 25.82 equals 49. So we're going to get F of T1 sine phi is going to equal 49 minus 75 sine of 25.82. So F of T1 sine phi is going to equal, that value is 16.358. This is where we're going to use a technique that we've already used this quarter. We're going to see it again. It's important to remember this, and it's on your formula sheet. When you see a sine of an unknown and a cos of that same unknown, this should trigger in your mind that perhaps we're going to need this. Tan phi is equal to sine phi over cos phi. And one of the techniques that you should have looked at in Foundations of Math Pre-Calculus 10, Form 10, or you did it in Pre-Diploma 10, or you would have seen it, you should have seen this at some point, is the idea that when we're solving equations like this, we can take one equation and divide it by the other equation. And that's the technique that I want you to see here, okay? We're going to have f of t1 sine phi equals 16.358 divided by f of t1 cos phi equals 75. Oh, and I have a value for this actually. F of t1 cos phi, that's this 75 cos 25.8 is actually 67.524. So it's going to be 67.524. So I can divide those two equations by each other. That's going to cancel out, and I'm going to get tan phi is going to equal 16.358 over 67.524, which means phi is going to equal the tan inverse of 16.358 over 67.524, and which is going to equal 13.6 degrees, which is almost done, because what we actually want is the tension in the first cable. So we want force of tension 1. So what we're going to do is we're going to take this value and we're going to plug it back into either, that should be T1. We can plug it into either of these two equations to get a result. It doesn't matter because these ones both have FT1 in them, and now we know phi. So we can plug those back into either equation, and we can see that, I'll plug it into the green one here, we can see that FT1 cos 13.6 equals 67.524, which means f of t1 is going to equal 69.57 newtons. And we're done. There it is, in all of its beauty. We used the idea of total equilibrium to show that my leftward forces equal my right, my ups equals my downs, and my clockwise torques equal my counterclockwise. We took each one of these as far as we could, these two, and then we went and looked at my torques and said, okay, where do I put the pivot? I put the pivot where it will eliminate a torque from a force I don't know. That's the force I don't know. We're going to eliminate that torque, so we put the pivot there. We then used the torques to find an unknown over here. We had we used these two expressions, F perpendicular R and torques equals FR sine theta. This is a very useful result. Add it to your formula sheet. Put it on the front so that you're not wasting space on the back here. Once we used the torques to find the angle, we plugged the angle back into these two equations, and then we have a system of equations where we had two equations, where are they, right here, and two unknowns. We didn't know FT1 and we didn't know phi. We can use this relationship here. This is a handy relationship to use to solve this system of linear equations using division, which is a technique you should have learned in Form 10. We use this technique, sine phi over cos phi equals tan phi, gives us the angle. We plug the angle back. It doesn't matter if we have two equations here, we can plug it into either one. I plugged it into the green one here, and it gives us the force for tension 1 equals 69.57. There's a lot. I'm not going to do the last example, but I'm going to talk about it here, so flip the page. We've got example 5 here. You know, when we're out of quarantine and you guys are going to parties, because you shouldn't be going to parties now because you're all under, COVID restrictions. A good physics party trick is to get men and women in a kneeling position on a flat surface, then place a short object, less than 10 centimeters, like a pop can, is close to the right height. It's a little taller, but it's close. Get a short object less than 10 centimeters, about 50 centimeters in front of their knees. Put the arms behind the back and try and knock over the object using their nose, then return back to the upright position. Women can usually do this and men usually cannot. Why is this? I'm not going to answer this yet. If you'd like to take a look at this, if you have time, this is certainly not a requirement. Try it at home on your own. Put a 5 centimeter tall object 50 centimeters from your knees. See if you can lower yourself to knock it over with your nose with your arms behind your back, and then raise yourself back up. Again, women can usually do this. Men usually cannot. Give it a shot. See if you can come up with a reason why. And if you're interested, come talk to me and we'll see what we can do. Comment. I want to put this in here. Comment on the assignment publicly in the Google Classroom, which I'm just going to abbreviate as GC, if you try it. About whether or not you could. There you go. So here's what I want you to do. Flip the page, your homework, try this. Comment publicly whether or not you can do it if you've got time. But what you must do is I want you to take a look at the following. I want you to do question 1 to question 4. So 1, 2, 3, and 4, this entire first page. And then I also want you to look at question number I should have said 1 to 5. I also want you to do 5. I want you to do 7. And I want you to do 8. You know what? I'll just rewrite this neater. 1 to 5, 7, and 8. That is your homework for this lesson. As always, comments, questions, concerns, please let me know. Good luck. May the force be with you.